continue with this, and we have the last speaker of today's morning session, Satoshi Nawata from Fudan University, and the title is Positive Science in Knots. But let me make an announcement first. We will have the conference picture right after this lecture. Okay, we'll come up here and we have a conference picture, and because we have a short break for lunch, so please just quickly get to the. We need to make the picture in about something like 5 to 10 minutes. Okay.
Yeah. Is there an organized lunch here, or we just each go?
No,
each go.
Yeah.
Okay. Good.
Okay. Yeah. Sorry.
Okay. Thank you very much for the invitation. I'd like to thank Tan and Stavros and the organizers for the invitation. So today I'm going to talk about some positivity in the knot invariants. Before going to the detail, I just want to thank the community on knot theory. Even though I'm a physicist, always the research in knot theory is a very and related stuff are very open-minded to the physicists like me. So I have been benefiting for discussion and invitation to the conference for a long time. So I really appreciate your open-mindedness. So very positive sign. One positive sign not here. So that's the first remark I want to make. Today I want to make another give you the at least two, hopefully if time permits, the three broad conjecture about the positive sign in knot invariance as a physicist. The first is the torus knots, and then the refined transform theory. The another topic is hopefully PT homology on torus knots. And if time permits, I would like to talk about some topology, how the relation between knot invariance and the so-called wild character variety with the irregular function. So let's first talk about the torus knot and refined transform theory. Some of you may already know about the refined transform theory, but let me briefly introduce what the refined transform theory is. So refined transform invariant of torus knot can be computed by the modular matrices. Here, so the P is a McDonald polynomial. McDonald polynomial. Usually the usual like a quantum invariance S1 invariance, the P is replaced by the show function, and T is equal. When you take a T equal to Q limit, you get the ordinary S and T matrix in the West-Zumina-Witten model. And so to compute the torus knot, you just introduce a knot operator, which is just conjugated by element of the S2Z matrix, whose entry is n and m, which satisfies the 2z relation, and the torus knot invariance is just the matrix multiplication by knot operator and the S matrix, and just multiply the matrix, and then so that's how you get the refined transform invariance. When you take the T equal Q limit, again this reduces the ordinary quantum invariance. And then my notation is if you have a bar, it's an unnormalized. And then, so the P is the McDonald polynomial is the refined transform invariance of the unknot. And if you don't have a bar, so it means normalized invariance. And it satisfies the following properties. So if you conjugate the color, transpose the color, so the Q and T are swapped, and you just multiply you just take the inverse. Okay, T and the Q are swapped, and then you just take the inverse. And also, there is a so-called exponential growth property about color. So if you have the color like a lambda times the fundamental weights of the SLN, so the transform invariance is grow as exponentially as a color, number of color. So for instance, if you have omega 1, take omega 1, it's just the symmetric representation. So lambda is the number of boxes in the single row. And when you take Q equal to 1 lambda, you just see the exponential growth. It is conjecture that so in the case of color is the lambda is rectangular Young diagram. Up to change of variable, it is equal to the Poincare polynomial Humfley PT homology. For instance, for triple and single box, if you follow the prescription given here, so what you get is the three monomials with positive signs and so on. So that if you go to the double box, you get the 9 term, and as you can easily see, there are 3 terms here, and if you follow the exponential growth, 3 square is equal to 9. So 1, 2, 3, 4, 5, 6, 7, 8, 9. So this is the one evidence of exponential growth property. But soon after, this was introduced by Ganagi, Shakirov, and also in mathematical side, Cherenkov defined rigorously by using double fine algebra, and they soon realized that if you specify lambda is the Fuchs-like representation, non-rectangular, what you get is minus sign. Okay, so it's no longer it cannot be interpreted as a Poincare polynomial of the Humfley PT homology. So the question is how you get the positivity from the refined Chern-Simons invariance. Here comes physics. So my proposal is one can relate the refined Chern-Simons invariance, so-called enumerative invariance in the Calabi-Yau 3 form with some Lagrangian brane. So which is called a geometric transition or Lagrangian duality, as you might have heard of it. So the geometric transition tells you the equivalence of partition function. So one side is so-called it's called T star 3, sometimes it's called deformed conical, and the other side is called resolved conical. So the left-hand side here is the deformed conical, and the right-hand side is the partition function of the resolved conical. On the left-hand side, so deformed conical side is just the generating function refined Chern-Simons invariance, where lambda takes any color. And the G lambda is actually coming from the inner product of McDonald polynomial. And then right-hand side is the S is a Schur function, and then it has the partition function or generating function of the topological string theory, or resolved conical side would take the following form. And so the physics tells you that the F here, F and FQ and FT bar has the following the expansion where the FQ is a multiplication of M times F hat, and the FT is also M times F hat, but take a different value. T and Q are different. And where M is the matrix which is, C is the Krebs-Gordon coefficient of the symmetry proof, and B is some monomial when the sigma is the Fuchs representation. And if you take, if you use this identity, this F can be written in terms of some combination of this refined Chern-Simons invariance. And furthermore, if you use the physics argument, so this F hat is actually given here. F hat takes the following expansion. So the F hat is equal to charges means the sum of all indices, rho, g, beta, gr, and so on. And where the g is the meaning of genus, and the jr is as I'm going to explain, and beta is how the Riemann surface G wraps on the P1 in the resolved conical. Then, what we observed that all the example in refined Chern-Simons theory. Sorry, I'm still having trouble with using this machine, this n hat is always non-negative integers. So therefore, if you use refine non-negative integers, and then furthermore, if you use the physics argument, this n hat can be related to so-called the modular space of the so-called M2 and Feynman states, which takes the following the configuration. So here, so you have the map from open Riemann surface genus G, and the handle is the boundary is mapped to resolve conical, and if you take the Jacobian, it's favored over the modular space, and this the manifold is, if you take the cohomology group, a dimension of cohomology group, you get n hat. So therefore, if you use the refined Chern-Simons theory and the large n duality, so one can extract the information of the some enumerated invariants from the refined Chern-Simons theory, and which is always non-negative or positive. So that's one way to extract the positivity from refined Chern-Simons theory. And I think, as you might have heard of it, so this n hat is kind of the categorification or refinement of so-called Lavoisier-Marignan-Ogri-Buffer invariants. Okay, so the open problem to mathematicians. So they define this n hat, a dimension of this modular space. In fact, the closed version, so if you don't have the Lagrangian submanifold here, so here, so Lagrangian submanifold, there's a brane, so-called brane here. If you don't have Lagrangian submanifold, it's called the cross invariant, and this cross invariant version is already given by Panderban, Thomas, and Malek and Toda, which lies on algebraic geometry. But if you have a Lagrangian brane, so it's a territory of simplex geometry. So the invariance has not been defined yet, but hopefully one of the audience here can define this n hat. So this is the one aspect of positivity coming from refined Chern-Simons theory. Okay, any questions so far? So another the subject I'm going to talk about the Humphrey-Petit homology on non-torus knot. So in particular, I'm interested in so-called double twist knots, which is the class of non-torus knot except the triple. So here is a picture of the double twist knot. When m and n are equal to 1, it's triple, but apart from them, it's a non-torus knot. And I'm going to propose the Poincare polynomial Humphrey-Petit homology of this double twist knots in the case of when the color is rectangular. So let's consider first the figure 8 knot. So the figure 8 knot, the Poincare polynomial Humphrey-Petit homology is given here. The 4 terms. When you take t is equal to -1, you get the Humphrey-Petit polynomial usual. So you have the uncolored figure 8 Poincare polynomial, which has 5 terms, and then so in the diagram below, I think you might have seen it. So I just put the 5 dots here. Each dot corresponds to the monomial in the Poincare polynomial. So for instance, 1 corresponds to here. So I'm sorry. So the vertical line is a degree, and the horizontal line is q degree. And so the number above on the dot is a t degree. So for instance, 1 corresponds to the middle dot, and the a squared t squared corresponds to this dot, and 1 over a squared t squared corresponds to this dot because of the, if you read off, I'm sorry, I think I made something. Yeah, I'm correct. So this dot and so on. And in particular, so schematically, so the Poincare polynomial figure 8 can be understood as middle plus this triangle. Middle plus this triangle. So that's the schematic diagram. And then furthermore, if you go to the 6-1 knot, you just add one more triangle in the Poincare polynomial. So 1 plus the black triangle and the blue triangle, and so on. So if you keep increasing the number of foot twists, you just add this diamond in the vertically. You just keep increasing the diamond in vertically, a degree. Okay. That's how it works. And there's a small dot here is 1, the first one. And I'm interested in to compute the colored version of the Poincare polynomial, and in particular, so if you the Homolfini homology obeys so-called the exponential growth property in the color. So if you increase the number of boxes in color, it the dimension of homology increase the exponentially in terms of the number of colors. So therefore, roughly speaking, so the colored version of figure 8, colored Poincare polynomial, is for figure 8 is 1 plus diamond to the number of box lambda. I'm sorry, what I'm doing here. Oh gosh. Okay. And also, so the 6-1 case is 1 plus black diamond and blue diamond to the number of boxes in the Young table. That's roughly what happened in the Poincare polynomial. So the similar situation happened in the Chern class in the vector bundle of the variety. So let us consider the vector bundle, complex vector bundle of rank R on the variety X. So let's call E the vector bundle. And the Chern class is the by splitting principle and Chern class is actually a product of the 1 plus Chern root. Okay. And if you bring another vector bundle of rank S, so the Chern class is 1 plus another Chern root of F. Okay. And if you take the tensor product, of the E and F and take the Chern class, so what you get is the product of 1 plus X plus Chern root. Okay. That is very similar to what we saw in the previous case. So you just replace this diamond by X and blue diamond Y. What you get is exactly this formula. Okay. This, roughly speaking, this formula. And if you look at the top Chern class of this tensor product, so what you get is the only, you just remove one part and you just look at the X plus Y, which is very similar. I mean, if you just take the normalization, which is very similar to the case of figure 8. Okay. And so this formula is closely related to so-called special functions. For instance, the product of xi plus yj can be related to so-called the Cauchy formula. By using Cauchy formula, so you just sum over all the Young tableau inscribed by this rectangular Young tableau. R to the S is a rectangular Young tableau, and then multiply the Schur functions. Okay, Schur function lambda, and they take transpose, and what you get is the product of the top form of the top Chern class of E tensor F. And then furthermore, so if you consider all the Chern class, what you get is 1 plus X plus Y. And so if you use the Cauchy formula, you get this this formula. But so S lambda is a symmetric function. But so therefore, so symmetric function can be always expanded by the Shor function. So therefore, so there's the theorem by Lasko telling that the Shor function 1 plus x can be expanded by d times s, where d is given by this determinant of the binomial. So when you take lambda is a symmetric function, symmetric representation, the single row. So this is exactly the binomial theorem. So when lambda is single row, it's just number. And so in the case of symmetric function, you don't need to consider about the determinant, and you just consider the binomial, and what you get is the binomial theorem of the. But if you so therefore this formula can be understood as a generalization of the binomial theorem, and then so you can compute the Chern class of the E tensor F by using the Shor functions. Okay, so I just want to apply this method to compute the colored version of the Poincare polynomial of this double twist knots. So in the case of the Poincare polynomial, as we have seen, so it depends on Q and T and A. So therefore, so what we need is the so-called QT version of this QT version of these symmetric functions, which is again the Maclaurin polynomials. The QT version of the Cauchy formula is given by the sum over all the I'm sorry, this is R to the S. Sorry. So this rectangular Young tableau, and the lambda is inscribed by this rectangular tableau, and you sum over all the Maclaurin polynomials. What you get is the top Chern class of E tensor F. And furthermore, so the binomial theorem is generalized by so-called by using the shifted Maclaurin functions by Okunkov, and here is the formula. So P is the Maclaurin polynomials, and the P mu star is so-called shifted Maclaurin polynomials. And when you take the lambda is the symmetric representation, single row, what you get is Q binomial theorem. So this blue part becomes just Q binomial, and P mu is just some x1 to the n, and this becomes usual x1 minus 1 times x1 minus q, and so on. So you get the, when you restrict yourself to the symmetric representation, you get the Q binomial theorem. So therefore, motivated by this theorem, binomial theorem by Okunkov, I will introduce so-called the twist factor as follows. So-called the B is called twist factor, and this blue part is exactly what we have seen in this the QT version of binomial theorem. So this is you need to multiply some exponent, but which is complicated, but I'm going to suppress because of it's just to make it complicated in the form. So I just want to explain. So this is exactly the generalization of Q binomial in QT version of binomial. And the Poincare polynomial of the figure 8 and 6(1) knot for the rectangular tableau, I conjecture as follows. So you just insert this twist element into here, here to multiply by the two copy of them, and then you just multiply so-called the factor which depends on A. And here product is taken over all the content of the Young tableau, lambda. And so you have to sum over all the Young tableau inscribed by rectangular. I'm sorry, this is not R to the square, R to the S. Sorry, R to the S. I'm sorry.
What is sigma?
Sigma is if you consider the triple graded homology, you just replace by Q or T. Q or T. But if you go to the quadruple graded homology, as you know, you have to replace by capital Q3 something. And if you increase the braid, a full twist, you just multiply, insert this twist element multiple times. Okay. So here, I'm sorry, instead of R square, my notation is the RS. This is just a Young tableau, which R times S. So this rectangular tableau. Oh my goodness, I went too much. Sorry. Okay. So if you add the full twist, you add the twist element, and you just sum over the Young tableau inscribed by lambda 1. Okay. And you just keep going. Okay, so the general formula of double twist knots of the colored by rectangular Young tableau is just insert twist element twice and multiply the common factor. Where the twist factor is just the bunch of multiplication of this twist element. So M and N are the number of full twists, as we saw before. M and N are the number of full twist here. So this is the generalization of the Habiro's cyclotomic expansion. And then after change of variable, what you get is the positive coefficients after change of variable. And so this is a conjecture, and so we just check various property of the repeated homology should satisfy, and all the example we have checked a number of examples. So we just get all the example we saw they satisfy the properties, and furthermore, what's nice is that each summand is actually a rational function of the A, Q, T, and sigma. However, if you sum over all the Young tableau inscribed by rectangular Young tableau, what you get is the Laurent polynomial with positive coefficients. So we just found that this should be the right answer, but however, we don't understand the meaning or why this has to be true and so on. We even didn't prove the positivity of this. If you sum over all the inscribed by rectangular Young tableau, we didn't even prove the Laurent polynomial. So this is I will leave it to as an open problem. Okay, as a physicist. Okay. So this formula strongly suggests that as follows. So recently, new definition of the uncolored repeated homology is given by the Gorski, Nigut, Rasmussen, and Oblonko, Rosansky as follows. So they construct, so given the braid beta, so they construct so-called QT equivalent shifts over the Hilbert scheme of points on the affine plane C2. And they just take QT equivalent shifts, and they just take the shift cohomology of the Hilbert scheme points. And what you get is the uncolored repeated homology of the associated braid beta. Okay. So the QT degree comes from this equivalent degree, and the A degree comes from here, and the T is indeed the so-called tautological bundle of the Hilbert scheme points. So the uncolored version is given. So there are two different definitions. So one is so the Oblonko-Rosansky is so-called equivalent metric calculation, but it's just the different way of saying the QT equivalent shifts. However, so this is the uncolored version. Colored version has not been defined yet. So the formula we found as strong suggests as follows. So if you define the colored version of this repeated homology, So the prediction is when the beta is the two-strand braids. Two-strand braid. So the H lambda beta will give you the so-called realization of the so-called shifted McDonald polynomials. What we have seen, it is P star. So this beta will be added. Added inside the summon, multiplied inside the summon, because when you increase the number of foot twist. Foot twist. So therefore, this formula strongly suggests that if you define this colored version of the Qt equivalent shifts over Hilbert scheme, so after the Grothendieck-Lehmann log formula, what you get is a geometric realization of the shifted McDonald polynomial. So this is a suggestion from this formula. So so this is one open problem I would like to propose to the mathematicians. To realize, or this our formula can be motivation or like a guiding principle to define this colored version of the Humphrey PTA homology over the Hilbert scheme. Any questions so far? So what time it is? How much?
Around 23 minutes.
Okay, we can have time. So this is the non-torus knot. So the positivity and non-torus knot. Okay. So I'm going to move to the twisted wire character variety. Any other questions so far?
I do have a question.
Yes.
If you go back a few slides.
Yes.
Yeah, here. No, sorry. One further, I think. No, the one where you make a conjecture about very polynomial for general lambda. Yeah,
this one.
So if you sum
Okay.
over all lambda here
Yep.
in the second equation,
Yep.
do you have a proposal for a right-hand side where you sum over an m tuple of partitions which is unconstrained, so it doesn't have any nesting condition? So here on the right-hand side you have n somehow nested partitions.
Yes.
Do you have a version of that formula where this condition is dropped? It's just a free sum over n tuples of partitions?
I haven't tried, but I'm pretty sure you won't get the Laurent polynomial. Yeah, it's just rational function. Any other questions? Okay, so I'm going to move on to the twisted wire character variety. So the main object I'm interested in is so-called the modular space of flat connection with twisted irregular singularity on the sphere. So that the data as follows. You just I'm sorry, I'm still having trouble with these devices. You just start with the one structured sphere, and then given a triple and R. So we just study the modular space of the bundle with connection with following data. So V is a bundle of rank n, which is R times L, over the, sorry, not C, this is P1, so P1. And A is a flat GLN connection on the vector bundle V with the pole order n at P. So therefore, this connection around the pole P, it takes the following value, where Q is given by Z to the 1 minus n, and then so on. And so when n is equal to, let's see. Yeah, so when n is positive, this is the so-called more than the singular pole. So therefore, it's the irregular. It's called higher order pole. It's called irregular, or sometimes wild singularity. So the name twisted comes from this J. E takes the off diagonal. So the twisted means this Laurent tail does not have a coefficient in Cartan Savage of GLN. So therefore, the diagonal element is just 0. But the residue in the residue here is actually block diagonal matrix. So this is the data, and I'm interested in the topology of this wild character variety. And I mean, moreover, so the topology, so it's a complex variety, so one can introduce so-called weight filtration. Then it takes the so-called weighted Poincare polynomial, and here's the weighted Poincare polynomial. The reason why I put the I over 2 and the I runs for the even value is that the even and the next order, the weighted filtration will give the same, the isomorphic, the cohomology in the wild character variety. So I'm interested in this weighted Poincare polynomial, but so it's with the current technique, it's almost impossible to compute this object. But if you use so-called the duality, so-called non-abelian Hodge correspondence, and also spectral correspondence, so one can construct out of this S twisted irregular wild character variety, one can construct non-compact, non-toric Calabi-Yau threefold Y. This is black box, which I count on heavily on my collaborator Tony Pantev and Ron Donaghy, such that the topological string partition function of this Calabi-Yau threefold or generating function refined stable pair can be written as follows. So log of this Z is the generating function refined stable pair is equal to the following so-called Gopakma buffer expansion, where WP is this weighted Poincare polynomial. And moreover, so if you study this Calabi-Yau threefold, one can associate, if you do the localization technique, one can associate the topological vertex associated and not given here, and also the torus L, n minus 2 L minus 1 torus knot on the other side, on topological vertex. So therefore, this Z, the topological string partition function Z, can be computed by just drawing the refined Chern-Simons invariance I introduced before. The P is the unknown invariance of this McDonald function is associated unknown invariance. The refined Chern-Simons invariance on the right hand as associated to the torus knot associated with this right diagonal. And you just sum over all the Young tableau with adding some T element, T modular matrix. And if you, so this, using this topological string partition function, and then they compare with this weighted Poincare polynomial, and with this the refined Chern-Simons invariance, one can extract the information of the weighted Poincare polynomial, which always has a positive coefficient. So U and V are the variable which you sum over, and so this is the information you can carry out. And when you take the certain limit U is equal to V, so you get the so-called the E polynomial, which is introduced by the Thomas Hauser, and one can check the computation done by Thomas Hauser, and then you can just we just match. We have a match. So this is the information you can get out of the knot invariance by using physics. I think I'm running too fast. I think thank you very much for listening.
So questions, comments? Yes, so the Poincare polynomial is another way to say super polynomial.
So if you take when the case of when the color is specified by this rectangular tableau, after you change your variable, you get a super polynomial from refined transform interval.
So it's a triple graded, not a quadruple.
It's triple graded. And in particular, refined transform will give you so-called TC.
And it's rigorously defined for every node.
So this refined transform is rigorously defined by torus node. Only torus node. It can be defined only torus node, but not non-torus node.
Yeah, but what is the point? I mean, torus node should be determined by just two numbers, so you can just define anything from two numbers, and then you can declare that to be invariant of the torus node corresponding to those two numbers, right?
Yes.
Well, any other questions or comments?
So I remember a talk, I'm not sure, you told me that there's a version of refined transassignments also for knots that are embedded on hygiene surfaces. Then there are some knots which appear as torus knots, and then also as pretzels, which can go on these two surfaces. And if you compute the refined transassignments in there, in these 2 seconds, it's actually the same answer. So there's something.
Yeah, that's something.
I also have a question.
Yes.
So it's only peripherally related to your talk, but you mentioned that the reduced Humphrey polynomials of knots that you showed us consist of these diamonds, a certain number of diamonds, and then a single one.
Yeah.
And in general, I think it's there's experimental evidence that you always see diamonds and zigzags, right? And you have the extremal case of the zigzag is a single. Do you understand from like this grown-up BPS capping perspective what the number of diamonds and zigzag means? Or the length of a single zigzag that you see for a knot and the number of diamonds?
Good question. To be honest, I don't know. Yeah.
But here for these twist knots, you have a prediction about how many diamonds appear.
Yes. So if you increase this foot twist and then there's two strand foot twist, you get a diamond, and you just keep increasing if you increase foot twist, and this exponential growth is captured by this interpolation Markov polynomial. That's my conviction. Yes.
But the number of diamonds is not expected to be a topological invariant.
No.
Depends on presentation.
Yeah.
Even zigzag can be understood as the diamond minus point, right? So it depends on interpretation.
Okay. Any more questions or comments? If not, let's thank Satoshi again.